another presentation from Electronics Engineering, graduating batch of 2016-2017. I am Eugene TOLENTINO, and I hope you enjoy watching this video.
Hi, I'm Jason.
I'm ERIKA.
I'm Eugene.
I'm John Mark.
I'm ANDREA. We are the representatives of Polytechnic University of the Philippines, Santa Rosa Campus.
We are here to present our thesis study under the supervision and advisory of Engineer ROSELITO E. Tolentino.
Our study is entitled
Application of Tri-Axial Accelerometers and Magnetometer in Mimicking a 3-degree of freedom robotic shoulder using vector multiplication and field compensation algorithm.
In the recent years, the development of interaction between robots and humans has become a key research topic in the field of robotics. Mimicking robotics is one of the most important applications in the vast field of robotics, whereas the robots are being controlled by specific human movements. Methods and techniques had been developed and different sensors had been used to capture human motion to manipulate the movements of the robot. A lot of robots today used high-cost integrated force torque sensors and cameras in order to detect human motion. However, the most common and cheapest of these sensors were the accelerometers and magnetometer.
Accelerometers can determine the position and orientation of an object. It was used to sense not only the gravity but the sudden acceleration within a range of motion. On the other hand, magnetometers measure the direction and strength of magnetic field along one dimension. It can be used to detect Earth's magnetic field, which always points to the north. This reference contained the horizontal component from which it is possible to read off lateral orientation of the device, unlike the accelerometers. Combining these two sensors, it was possible to acquire angles that can be used to mimic human motion.
A research entitled Application of Vector Multiplication Approach for Point-of-View Variations in a Mimicking Robotic Shoulder using Microsoft Kinect, which attempted to create solutions to accurately translate human motions in a robot using Kinect sensor. The proponents solved the problem of the previous studies by designing and implementing a new algorithm based on vector multiplication approach.
Another research work entitled Application of Scalar Product for Acquiring Angle in Mimicking Robotic Elbow using two Tri-Axial accelerometers had determined the angular position of the elbow joint. This study also acquired elbow angle by using the data from the accelerometers to control the robotic elbow. The data was gathered through a test of the user's varying elbow angle in different orientation. This study also aimed to evaluate the mimicking capability and the response of the robotic arm with respect to the controller.
A research work entitled Human Joint Angle Estimation with Inertial Sensors and Validation with a Robot Arm combined kinematic models designed for control of robotic arms with state-space methods to estimate angles of the human shoulder and elbow using two wireless wearable inertial measurement units. Velocity and acceleration were tracked and propagated from one limb segment to another using Newton-Euler equation implemented in state-space form. Their proposed algorithm was tested on a 6DOF industrial robotic arm.
The previous researchers only acquired the pitch and yaw angles. They did not use these angles for the purpose of mimicking the human shoulder movement. The shoulder joint was also limited to 2 degrees of freedom, which cannot mimic the human shoulder correctly. The proponents analyzed and discovered that accelerometer was able to track human joint angle, specifically the elbow. The problem was that the previous researchers only acquired 1 degree of freedom. Most parts of the human body required more than 1 degree of freedom movement. Therefore, it was essential to acquire more than 1 degree of freedom movement to properly mimic other parts of the human body.
To solve the problem of the previous study, the proponents applied the accelerometer sensor to mimic a 2DOF, the pitch and roll movement of the human shoulder using vector multiplication. The magnetometer and accelerometer sensor was applied to mimic the remaining 1 degree of freedom, which is the yaw movement of the human shoulder using tilt compensation algorithm. The proponents used accelerometers that were attached to the spine, right shoulder, upper arm, and lower arm in slanting position. The magnetometer and accelerometer pair was specifically placed at the top of the shoulder joint.
The figure illustrated the concepts and ideas that were involved in this study. The accelerometers and magnetometer were attached to the user. The proponents were able to get the digital output from the accelerometers using Arduino and use the data to construct vectors for pitch and roll. Vector multiplication was used to acquire pitch and roll movement needed for the servo motor to actuate the movement of the robotic shoulder. Also, the proponents were able to get the digital output from the magnetometer-accelerometer pair using Arduino and use the data to construct vectors for yaw. The process of tilt compensation algorithm was used to acquire the yaw movement needed for the servo motor to actuate the robotic shoulder movement.
The proponents used Labio Robotics to do the computation. The angles of pitch, yaw, and roll will be sent out to Arduino and then to the actuator, which was the servo motor.